So we're going to turn our attention now to computing the surface area of parametric surfaces. And so it turns out that the area of a parametric surface S, given by, parameterized by R of U and V over some region D, is just, well, it's just A equals the double integral over D of the length of R partial U cross R partial V dA. And by the way, this is happening in the over the UV plane. D is in the UV plane. So your variables, whatever variables U and V you're using, that's the default variables for your integral. One quick word, just a brief connection here. I'm not going to justify why this holds in this video, but I do want you to remember that we interpreted the length of cross products as area of little parallelograms before, and that actually is kind of what's happening here. These are approximation. You're looking at little approximations using the parallelograms, and when you add them all up in the right way, you get the surface area that we want. So let's do an example. So I want to find, just to set up the integral that gives the area of the surface with these equations. And so we're not even asked to compute the integral. I'll show you why I didn't ask you to actually compute it in a few minutes when we get there. Let's hopefully it's clear to you that our function R of U and V in this case is just 2UV, U plus V, and U minus V. And so we need to compute R partial U, and we're going to get what? 2V, 1, and then 1. And we want to go ahead and compute R partial V, and we're going to get 2U, 1, and then minus 1. And I write them stacked like this on purpose. That way when I go to take their cross product, it's easier for me. I've got everything written in a nice way that allows me to take their cross product. And so let's do it together. So I'm going to get minus 1 is what? Negative 2. Then I'm going to get minus, and then it's going to be negative 2V minus 2U. So I'm going to take the negative of that and get, I'll say 2U plus 2V, whatever. And then I'm going to, for the last one, I'm going to get 2V minus 2U. So 2V minus 2U. Hopefully we can squeeze that in. There we go. So pop the 2 out, and you're going to get a 2 times negative 1 U plus V, and then V minus U. You don't want to drop the 2 when you're setting up these integrals. If we were just looking for the normal vector, I could drop this 2, but I do need to keep it and take the length of this guy. Although keep in mind, when you take the length, you can just pop the 2 out. So this is going to, when I'm looking for the area, I'm going to have the double integral over the whatever region D that R of U and V is defined for, of the length of the cross product RU and cross RV. So I'm going to get the double integral. Let's think about it with me. I want to take the length of this guy, of this whole thing. So I'm going to get a 2 times the square root of what? 1 squared plus U plus V squared plus V minus U squared. And then I can just put a dA if I want, or I can go ahead and integrate this. Let's say du dv. It turns out that our bounds here are all constant. This is just a rectangle, so it doesn't really matter the order. U is going to go from 0 to 2, and V is going to go from 0 to 1. And we can simplify this a little bit. You can write this as pull this 2 out. By the way, this 2 is just this 2, to make sure we're clear. Pull the 2 out, and we're going to go 0 to 1, 0 to 2, and we're going to get 2u squared plus 2v squared plus 1 du dv when you combine all the like terms here. Now, I'll tell you right now, that's a nasty integral, and I put it in Mathematica just so you could see what the answer is. And this is the precise answer to that integral. Wow, who knew? And so quite difficult, but it's roughly equal to 7.98364. So that's the surface area that you get. So I'll break this video here, and then I want to show you a special case of these surface area type problems, and we'll probably do 1 or 2 more examples.